Welcome to Wisdom Docs. Settle in. Let the room go soft around you. There is nowhere you need to be tonight, and nothing you need to solve, and no thought you need to finish. Let your shoulders come down from wherever they have been holding all day. Let the weight of your body sink a little further into whatever is holding you. We are going somewhere slow and very old tonight, somewhere deep beneath your feet. And you do not need to stay awake to arrive. You can drift off anywhere along the way. The story will keep going without you, the way the planet does, the way it always has. Somewhere beneath the floor of an ocean, right now in the dark, a slab of stone is sliding down into the earth. It moves about as fast as your fingernails grow. You would never see it move if you stood and watched for a lifetime. But it is moving, slowly, patiently, the way everything down there moves, and it is carrying something with it. On the back of that sinking slab is a layer of pale rock, limestone, made from the shells and skeletons of small sea creatures that lived and died and drifted to the bottom over countless quiet years. Limestone is, in a sense, frozen breath, the carbon that was once in the air, once dissolved in the sea, once gathered up by living things, has been pressed and stacked and turned to stone, and now that stone is going down past the edge of a trench, down beneath the lip of a continent, down into the hot interior of the world, where the heat and the crushing weight will do something remarkable to it. They will cook the carbon back out of the rock. And after a long, long while in some distant volcano, that carbon will rise again as gas, as a slow exhalation through the throat of a mountain, and rejoin the sky. This is the down escalator and the up escalator of carbon. The seafloor rides down, the volcano breathes it back up, stone in, breath out, around and around for 4 billion years. And tonight, very gently, I want to ask you a strange and enormous question. What would happen if that movement simply stopped? If the slabs stopped sliding, if the escalators stopped turning, if the whole great machine of plate tectonics fell still and quiet beneath us? Not in a flash, not in a disaster, not in a single terrible afternoon, but slowly, across deep geological time, the way real things change down there. What would become of the world? Most people, when they hear that question, picture the obvious things: no more earthquakes, no more eruptions, mountains worn down to gentle hills over the ages. And those things are part of it, yes, we will get to all of them in their own time tonight. But that is the surface of the answer, the shallow part, and the real story runs much deeper and is far stranger. Because plate tectonics is not only the thing that shakes the ground and raises the peaks, it is, quietly, the planet's thermostat. It is the planet's recycler. It is the slow, patient machine that has kept this world livable for almost its entire existence, and almost nobody thinks of it that way. We are going to spend tonight following that thread down into the dark, and what we find at the bottom is not a story about earthquakes at all. It is a story about a single ancient feedback loop that has been gently holding the temperature of the whole Earth in balance, the way a hand on a dial keeps a flame from going out or flaring too high. And we are going to ask, what happens to that hand when it lets go? So let us begin with the breathing. Let us begin with the air. There is a slow cycle that governs the carbon in the sky over millions of years, and it works like this. Rain falls. It is faintly acidic because as it falls, it picks up a little carbon dioxide from the air and becomes the mildest, gentlest acid you can imagine, far too weak to harm you, far too weak to feel, but it is strong enough, given time, given endless patience, to attack rock. When that faintly sour rain lands on the silicate rocks that make up most of the continents, it begins, very slowly, to dissolve them. Imagine a sugar cube under a dripping tap. not crumbling all at once, but wearing atom by atom, year by year. This wearing away of rock by rain and carbon dioxide is called silicate weathering, and it is one of the most important processes on Earth that you have probably never thought about. Because here is the quiet miracle of it. When the rain weathers the rock, it pulls carbon dioxide out of the air. The carbon leaves the sky and combines with the broken down rock, and the rivers carry the result down to the sea. There, sea creatures take it up to build their shells, and when they die, those shells settle to the ocean floor and become limestone. The carbon that was in the air is now locked in stone at the bottom of the sea. So weathering is the planet inhaling. The rock breathes in the carbon dioxide, draws it down out of the atmosphere, and buries it as limestone on the sea floor. That is half of the cycle, that is the inhale. And the exhale, you already know because we started there. The limestone rides down the down escalator, down a subduction zone, where one slab of the planet's outer shell dives beneath another and sinks into the hot interior. The heat and pressure bake the carbon back out of the stone, and it rises and eventually it escapes through volcanoes back into the air as carbon dioxide once more. That is the exhale. The volcano breathes out what the rock breathed in. Inhale, weathering. Exhale, volcanoes. Around and around. Scientists call this the carbonate-silicate cycle or the deep carbon cycle, and it is the long, slow lungs of the world. It does not breathe on the scale of a human chest, in and out across a few seconds. It breathes across millions of years, one enormous geological breath that takes longer than the whole of recorded history to complete. But it breathes. And as long as it keeps breathing in and out in balance, the amount of carbon dioxide in the sky stays roughly steady. And the amount of carbon dioxide in the sky is, more than almost anything else, what sets the temperature of the planet. Now here is the part that turns this from a curiosity into a kind of wonder. This cycle does not just breathe, it corrects itself. It self-regulates. And the way it does that is the heart of everything we are talking about tonight. In the year 1981, three scientists, James Walker, Paul Hayes, and James Casting, described this self-correcting behavior in a paper that has shaped how we understand our planet ever since. We call the idea the weathering thermostat or the Walker-Hayes-Casting feedback. And the reason it deserves the name thermostat is that it works exactly like the thermostat on a wall in a cold house, the little dial that keeps the room from getting too hot or too cold by turning the furnace on and off. Follow how it works, slowly, because it is beautiful. Suppose the Earth begins to warm up. More heat means more evaporation, more rain, and warmer temperatures make chemical reactions go faster, just as warm water dissolves sugar faster than cold water does. So a warmer Earth weathers its rocks faster, and faster weathering means more carbon dioxide pulled out of the sky and buried, and less carbon dioxide in the sky means less warming, so the planet cools back down. The warmth, in other words, triggers the very process that cools it. The fever sets off its own cure. Now run it the other way. Suppose the Earth begins to cool, to slide toward ice. Cold slows everything down. The rain is sparser, the reaction sluggish, the weathering crawls. So less carbon dioxide is pulled out of the sky. But the volcanoes keep breathing out, steadily, indifferent to the cold. And so carbon dioxide begins to build up in the atmosphere, unmatched by the slowed down inhale. And more carbon dioxide means more warming. So the planet warms back up out of the cold. The chill, in other words, triggers the very build-up that warms it. The shiver sets off its own blanket. Do you see what that means? In both directions, the system pushes back toward the middle. Too hot, and it cools itself. Too cold, and it warms itself. It is a negative feedback, which is just the scientist's name for a loop that quiets itself down, that resists change, that always nudges the dial back toward a livable setting. This is the thermostat. This is the gentle, mindless, 4 billion year hand on the dial. No one is turning it, no one designed it. It is simply what happens when you have rain and rock and volcanoes and a planet patient enough to let them work on each other across the ages. And it has been working, more or less, for almost as long as the Earth has existed. To understand just how much we owe to that quiet thermostat, you have to know something strange and a little unsettling about the sun. The sun has not always shone as brightly as it does now. When the Earth was young, about 4 billion years ago, the sun was considerably dimmer than it is today by something like 30%. 30% less sunlight. If you took the sun we have now and dimmed it by nearly a third and shone that weaker sun on the Earth as it is today, the whole planet should freeze. The oceans should turn to ice from pole to pole. By every simple calculation, the young Earth under that faint young sun should have been a frozen ball of ice, locked solid, lifeless. And yet, it was not. We know from the rocks themselves that the young Earth had liquid water, had oceans, had rivers, had life beginning to stir in the warm dark of the sea. The planet was not frozen. It was, somehow, comfortable. This is one of the genuine puzzles of Earth science, and it has a name. It is called the faint young sun paradox. How could the Earth have stayed warm and wet under a sun too dim to keep it from freezing? And the answer, the leading answer, the answer that has held up for decades, is the thermostat. When the sun was faint, the planet drifted cold. And as we just saw, cold slows the weathering, so the carbon dioxide from the volcanoes built up thick and warm in the sky, an extra blanket laid over the young world. More carbon dioxide trapped more of the weak sun's heat, and so the Earth stayed warm in spite of the faint sun. And then, across billions of years, as the sun slowly brightened toward what we see today, the warming planet weathered its rocks faster and faster, drawing down that thick blanket of carbon dioxide, thinning it just enough to keep the temperature from climbing too high. The thermostat let out the blanket when the sun was weak and took it back as the sun grew strong. It tracked the brightening of a star across 4 billion years and held the Earth in the narrow band where water stays liquid and life can hold on. That is what this slow breathing has been doing all along, beneath our notice, while everything else we care about lived and died on the thin, warm skin above it. Scientists have built careful models of this long carbon dance, models with names like geocarb, developed by the geochemist Robert Berner, who spent much of his life trying to reconstruct how carbon dioxide and the carbon cycle have varied across the whole vast history of the Earth. These models trace the breathing back across hundreds of millions of years, the rise and fall of the carbon in the sky, the slow pulse of the planet's lungs. And what they show, again and again, is a world held in balance by this loop. A world that keeps coming back to livability because the thermostat keeps nudging it there. So now we have the machine clearly in view. 2 arms, one arm is weathering, the inhale, the rock-breathing carbon dioxide in out of the sky. The other arm is volcanism, the exhale, the planet-breathing carbon dioxide back out, fed by the down escalator of subduction carrying that carbon back into the depths to be cooked free and returned. 2 arms working against each other, and in their tension, in their endless push and pull, they hold the dial steady. They hold the temperature. They hold, in a real and literal sense, the habitability of the entire world. And here, at last, is where our question tonight comes back sharpened now, much sharper than it was when we began, because we asked what would happen if plate tectonics stopped. And now you can see that this is not really a question about earthquakes. It is a question about the thermostat, because one of those 2 arms, the exhale, the volcanic resupply of carbon dioxide, depends entirely on plate tectonics. It depends on subduction, on the down escalator, on slabs of carbon-loaded seafloor sliding into the earth to be cooked free and breathed back out through arc volcanoes. Take away plate tectonics and you take away the down escalator. Take away the down escalator and the carbon stops coming back. And if the carbon stops coming back, the exhale stops. One arm of the thermostat goes slack. But, and this is the quiet, eerie heart of it, the other arm does not stop. The inhale does not stop. The weathering does not need plate tectonics at all. It just needs rain and rock and time, and the Earth will have all three for a very long while yet. So, the rain keeps falling. The rock keeps wearing. The carbon keeps leaving the sky, buried as limestone on the floors of the seas. The planet keeps breathing in, but it can no longer breathe out. Sit with that for a moment in the dark as you drift. A planet that inhales and cannot exhale. A thermostat with one arm cut. It does not break in the way you might expect, sputtering, swinging wildly hot and cold. It breaks in a much stranger way. It runs in one direction only. The dial, no longer pushed from both sides, begins to slide steadily, quietly, irreversibly toward one extreme. The carbon keeps draining out of the sky and never comes back. And the only question that matters, is which way the planet tips when its breath runs one way. Let us put some sense of scale on this so you can feel how slow and how vast it is. How much carbon does the planet actually breathe out through its volcanoes? The figure is small in human terms and enormous in planetary ones. The volcanic and metamorphic outgassing of carbon from arc volcanoes, from the long undersea ridges where new seafloor is born, from the slow seeping of gas through the crust, adds up to something on the order of 1/10 of a gigaton of carbon each year. Roughly 60 to 100 million tons of carbon dioxide breathed back into the sky annually, though the exact number is debated and uncertain, as numbers about the deep Earth tend to be. It is a thin, steady exhalation, a trickle, but it has been trickling for 4 billion years, and it is precisely the trickle that balances the inhale, the slow drip that keeps the carbon dioxide in the sky from draining away to nothing. Cut off subduction, cut off the arc volcanoes that this resupply depends on, and that trickle collapses, fades, over geological time, toward zero. The exhale falls silent. And now I am going to open a door tonight and leave it open the way the planet leaves its great loop open, and we will walk through it later. Because the natural question, the question pressing on you now if you are still with me, is simply this: which way does it tip? A thermostat with only an inhale, a planet draining its own breath out of the sky and never breathing back, the carbon dioxide sliding lower and lower across the deep ages. Does the world freeze, the warming blanket pulled thin and then pulled away entirely, the planet sliding back toward the ice it was always one faint sun away from? Or does it bake somehow on a different kind of world, where the breath once ran the other way and the dial slid the opposite direction toward fire? Here is the strange truth, and I will only set it down gently here and return to it when you may already be asleep. The very same failure, the very same stopping of the great machine can tip a planet either way, toward ice or toward fire. The same broken thermostat holds two opposite graves, and which one a world falls into depends on where its breath was running when the machine stopped. And the most astonishing part, the part that should make the hair on your arms stand up except that you are too comfortable and too close to sleep for that now, is that we do not have to imagine either outcome. We do not have to guess, because there are two planets right next door, close enough that we have sent our machines to walk across one and to peer through the clouds of the other, two worlds that long ago lost the great recycling machine that Earth still has. And one of them froze, and one of them bakes. They are sitting out there tonight in the same darkness the Earth turns through, two ghosts of the two futures, two answers to the question we have only just learned how to ask. But they are still a long way off in our story, those two ghosts, and there is much to walk through first. For now, simply hold the image. The down escalator slowing, the slabs settling, the limestone that would have ridden down into the heat and come back as breath, lying still instead on a sea floor that no longer moves. The volcanoes, one by one, going quiet, their fires fed by a current that no longer flows. And above it all, the rain still falling, the rock still wearing, the carbon still leaving the sky, draining away one molecule at a time, with nothing, anywhere, on the whole, still planet, to give it back. The world inhaling, and inhaling, and inhaling, and never, ever breathing out again. The thermostat has two arms and only one of them keeps working. Tomorrow, or in a few more minutes of this quiet voice, we will learn which way the dial slides and what becomes of a green world when the carbon it lives on slips below the line that life itself requires. We will watch the mountains begin their long surrender, with nothing left to rebuild them. We will follow the planet into a stillness deeper than any silence you have ever known. But not yet. Not tonight. For now, there is only the slow breathing of the rock and the slabs sinking into the dark and the soft, patient turning of a world that has held itself in balance for longer than the mind can hold and is only now, in our imagining, beginning to let go. Let your own breathing slow to match it. In and out. The planet took 4 billion years for a single breath. You have all night for yours. There is nothing to hold up, nothing to keep turning, nothing to keep aloft. Let the dark be easy. Let the slow machine of the world carry the thought onward without you, down the long escalator, into the warm and silent depths where the carbon waits and the stone sinks, and the patient heart of the planet goes on, beating its slow and ancient beat, whether or not anyone is left awake to listen. Picture the seafloor then, not as a fixed thing, but as a slow river of stone, always moving, always heading somewhere. The carbon you breathe out tonight, the carbon a forest pulled from the air. 10,000 years ago, the carbon locked into the white cliffs of chalk and the grey shelves of limestone that paved the bottom of every ocean, all of it riding the same long current. Rain falls. Rain mixed with the faintest trace of carbon from the air, just enough to turn it the gentlest acid, soft enough to drink, patient enough to dissolve a mountain. It lands on bare silicate rock, the grey and pink and green of the planet's bones, and it pulls the rock apart molecule by molecule, and it carries the pieces down the rivers to the sea. There the shells form, the corals build, the white sediment settles, year upon year upon year, until the floor of the ocean is paved in the buried breath of the sky. And then that floor, that whole vast pavement of captured carbon, reaches the edge of a plate, reaches a trench, and it begins to ride down. This is the down escalator. Picture it slowly. A slab of old, cold, limestone-laden seafloor, heavier than the warm mantle beneath it, bending at the trench and sliding under the edge of a continent, down and down into the dark, into heat and pressure no human eye will ever see. And as it sinks, the heat goes to work on the carbon it carries. The limestone bakes. The carbon is driven out of the stone and it rises, it gathers, it pools beneath the crust, and at last it finds its way up through a chain of volcanoes and out into the open air again, as gas, as breath, as the planet exhaling what the rain inhaled 100 million years before. Slabs of limestone seafloor sliding down into the earth and coming back out as volcanic breath. This is how the planet has exhaled carbon for 4 billion years. In through the rain, down through the trench, out through the volcano, and round again. The deep carbon cycle, the slow lung of the world. And here is the thing nobody tells you when they speak of plate tectonics. They tell you earthquakes. They tell you the ground shaking, the cities falling, the fault lines drawn in red across a map. And all of that is true, and all of it is the smallest part of the story. Because the same machine that shakes the ground is the machine that runs the thermostat. The plates are not only the cause of the planet's violence, they are the cause of its mercy. They are the recycler and the regulator both, the thing that has kept this single world warm and wet and habitable across an unimaginable gulf of time against odds that should, by every measure, have left it dead. Consider what should have happened. 4 billion years ago, the sun was not the sun you know. It was dimmer, perhaps 30% dimmer, a fainter and younger star, and a planet sitting where Earth sits, receiving that thinner light, should have been frozen solid. An ice ball from pole to pole, white and silent and sterile, locked under a shell of frost too thick for any warmth to break. The faint young sun, the scientists call it, and the puzzle it leaves behind is simple and enormous. The sun was too weak to keep Earth from freezing, and yet Earth did not freeze. The rocks of that ancient time hold the signatures of liquid water, of rivers and seas, of a living warmth that had no business existing under so pale a star. How? How did the planet stay warm when the fire that lit it had barely been kindled? The answer is the thermostat, the same one. The weathering thermostat, worked out and named by 3 scientists, Walker and Hayes and Casting, in 1981, and it is one of the most elegant ideas in all of Earth science, and it is the quiet hero of this whole long story. So let it settle in your mind slowly. It works like this. When the planet grows warm, the rain falls harder and the rock weathers faster, and faster weathering pulls more carbon dioxide down out of the air. And with less carbon dioxide to trap the heat, the planet cools. And when the planet grows cold, the rain slackens and the weathering slows, and the volcanoes keep breathing carbon out into the air with no one to pull it back, and the carbon builds and the warmth returns. Warm makes cold. Cold makes warm. A loop that bends always back toward the middle, always toward the livable, a dial that turns itself. And when the sun was faint and the planet should have frozen, the cold simply let the carbon accumulate, thickening the blanket of the air, holding in what little warmth there was until the balance was kept. The thermostat did not need anyone to set it. It set itself across 4 billion years through the silicate weathering of the rocks and the carbonate building of the seas, the carbonate-silicate cycle turning slow beneath everything, the long arithmetic that the carbon models, the ones called geocarb, the ones traced out by Burner across the whole sweep of geological time, have spent decades learning to read. So the planet has 2 ways to put carbon back into the sky, and both of them lean on the moving plates. The volcanoes that breathe out the carbon the slabs carried down, the arcs of fire that stand wherever one plate dives beneath another, and the slow churn of the whole system that keeps that recycling turning. The numbers are small, almost absurdly small, for something that holds a world in balance. On the order of 1/10 of a gigaton of carbon a year, leaving the deep earth and entering the air. Somewhere between 60 and 100 million tons of carbon dioxide breathed out each year from the arcs and the ridges and the slow, diffuse exhaling of the ground. A trickle, a whisper, and yet across the long ages it is exactly the counterweight that the rain requires, the other arm of the balance, the breath that answers the inhale. And now, in our imagining, the plates have stopped. The escalator has halted. The slabs hang frozen at the lips of their trenches, sinking nowhere. And the arcs of fire that stood above them, fed for so long by the carbon riding down, begin to starve. Their magma supply, once renewed by every kilometer of seafloor that dived into the dark, has nothing left to draw on. One by one, across ages, they fall silent. The volcanoes that were the planet's exhale go quiet. But the rain does not stop. The rain never stops. It keeps falling on the silicate rock, keeps dissolving it grain by grain, keeps carrying the carbon down the rivers to the sea, keeps burying it in the white sediment of an ocean floor that no longer rides anywhere. The inhale continues. The exhale has ended. Silicate weathering goes on, stripping carbon dioxide out of the air, faithfully, relentlessly, exactly as it has for 4 billion years, and there is nothing now to put it back. The trickle from the deep earth has dried. The one arm of the thermostat still reaches and pulls. The other arm hangs cut and useless at the planet's side. A thermostat with one arm cut does not break in the ordinary sense. It does not simply stop. It runs. It keeps running, but only in one direction, only ever in one direction, the dial turning and turning and never turning back. The planet inhales and cannot exhale, the carbon draining steadily out of the sky and into the stone and never returning, and the long, slow, self-correcting loop that held this world in the livable middle for an age beyond imagining unwinds at last into something that can only fall. So here is the loop I will leave open for you here at the edge of sleep, the first of the questions this still planet asks. The thermostat runs in one direction now. The carbon leaves the sky and does not come back. And a world that loses its carbon slowly across 100 million quiet years is a world that tips. The only question is which way? Toward the fire or toward the ice? And the answer, when it comes, is stranger and gentler and more terrible than the simple word freeze can hold, because the line that life depends upon is not the line you would expect, and the world does not have to grow cold to grow lethal. Guess which way the planet tips. Hold the question lightly. You do not have to solve it tonight. Think about the carbon that is leaving the sky, one dissolved molecule at a time, one grain of stone at a time, each acid rain swallowed by the quartz and feldspar of the uplands, and emerging months or years later as bicarbonate ions in a river carried to the coast, deposited on the ocean floor, locked into limestone. The rain does not know it is doing this. The stone does not resist. It has been happening since there was rain and stone and the right minerals at the surface, and it happens now, and in the world we are slowly imagining together. It will go on happening for a very long time after the last arc volcano has grown cold and dark and silent, and the carbon does not come back. That is the whole of it, really. That is the clock that is now running in one direction. The planet has been breathing in and breathing out across geological time, and the outbreath depended on something happening 60, 80, 100 kilometers below the ocean floor, inside hot rock under enormous pressure, where limestone that had sunk down a subduction trench met temperatures that cooked it back into gas, and that gas worked its way upward through the roots of the island arcs, through the throats of the stratovolcanoes, and came out as carbon dioxide into the open air. That was the exhale. That was always the exhale. And now the throat is closed and the lungs of the deep earth are simply not delivering, and the inhale continues all the same. What happens to a room when you seal the window and run a fan that draws air out? The pressure drops, the room is not destroyed, not rearranged, nothing breaks, but it becomes a slightly different kind of room, and eventually it becomes a room nothing can breathe in. The atmosphere of this still world is becoming a slightly different atmosphere. 1 century at a time, 1 million years at a time, the carbon dioxide concentration nudging downward by amounts too small to measure across a human lifetime, but enormous across the patience of geology. You would not notice it in 1,000 years. You would not notice it in 10,000. But the models that trace this slow descent, the ones built from what we understand about weathering rates and burial, and the chemistry of carbonate minerals, those models suggest something quiet and devastating waiting at the far end of the timeline. There is a number that matters. It is not a cliff, not a wall, not a moment of sudden catastrophe. It is a threshold. And that threshold sits at around 150 parts per million of carbon dioxide in the atmosphere. Below that number, something stops working, not machines, not volcanoes, something older and more fundamental. Plants, or rather a particular and ancient and world-sustaining kind of plant. The ones that use what biologists call the C3 pathway for photosynthesis, which is to say, almost every tree you have ever stood under, almost every fern, in every rainforest, wheat and rice and barley and the grasses of the high meadows and the mosses on the north side of old walls. The C3 pathway, which has been running photosynthesis on Earth for hundreds of millions of years, depends on being able to pull carbon dioxide out of the air at a sufficient concentration that the biochemistry works. Drop the concentration below roughly 150 parts per million, and the machinery begins to fail. The enzyme at the heart of the process, rubisco, begins to make errors, grabbing oxygen where it should grab carbon dioxide, burning sugar rather than building it. The plant starves not because the sun has gone away, but because the air has gone thin in the one molecule it was built to eat. This is not a fast death. This is a dimming. Forests would thin at the edges first, the trees on poor soils or in dry climates, finding the margin too narrow, pulling back and not returning. The great boreal forests that ring the northern latitudes, the temperate woodlands, the fern understories, all of them quietly becoming less dense, less productive, less able to hold the soil that their roots have always held. Ecosystems do not collapse the way a bridge collapses, all at once with a sound. They withdraw, and the withdrawal looks at first like a bad year, and then like a bad decade, and then like the new normal, and then like a world that is simply different from the one before. James Lovelock and Michael Whitfield worked through this in 1982, tracing the long arc of the biosphere's lifespan given what the Sun is doing over deep time. And Ken Caldeira and James Casting extended those lines of reasoning, looking at what the brightening sun and the long-term changes to weathering rates mean for how much longer the biosphere can sustain itself. The picture that emerges is not the end arriving from outside, like an asteroid or a shift in the orbit. It is the end arriving from inside the system, from the feedback that kept life alive for 4 billion years, running past the point where it can be sustained. The weathering thermostat has been Earth's greatest gift, and in a world without volcanic resupply, it becomes something closer to a patient and implacable adversary. After the C3 plants, the ones that use the C4 pathway have a little more runway. C4 plants, which evolved more recently and include corn and sugarcane and many of the grasses of tropical savannas, have developed a way to concentrate carbon dioxide inside their cells before the rubisco gets at it, allowing them to work at lower atmospheric concentrations. They are not immortal in a low CO2 world, but they can survive where the C3 plants cannot. For a time then, a very altered, very diminished, very strange kind of vegetation might persist on the still planet. Grasslands where forests used to be, savannas where there used to be nothing, a world growing quieter and simpler and less productive at every scale, the food web thinning from the bottom the way a river thins in a drought, not suddenly but inexorably, the level dropping and the margin available to the creatures above it growing narrower season by season. And then the C4 plants find their floor too, and then there is less. This is the freeze that the thermostat with one arm drives toward, not the freeze of ice and glacier, not the snowball earth of deep geological history, though those temperatures might eventually come into range as well. First, and most fundamentally, it is the freeze of chemistry, the freeze of photosynthesis running slow and then slower and then failing. A world that cools in the sense that the biological engine at the base of everything cools first, The warmth of life withdrawing from the surface, the intricate noise of the food web going quieter, and the planet left to the patient, and simple chemistry of rock and water, and a thin sky that no longer holds what living things need to live. But wait, hold that image for a moment. The image of a cooling world draining toward biological simplicity, and then consider that the thermostat with one arm could also have tilted the other way. There is another planet in this solar system, nearly the same size as Earth, nearly the same mass, made of similar rock, close enough to the Sun that for a long time it was thought, even hoped, to be something like a twin. And on that planet, the thermostat did not run toward the freeze. On that planet, the thermostat did not run at all, in either direction. The sky of that planet is thick with carbon dioxide, 96% of the atmosphere carbon dioxide, and the surface sits at 465 degrees Celsius, and the atmospheric pressure at that surface is 92 times what you feel pressing gently against you right now. That planet is Venus. Venus is not a frozen world. Venus is the other grave. Venus is what happens when the CO2 keeps accumulating and the drawdown mechanism fails to compensate. It is the bake rather than the freeze, the fire door rather than the ice door, and it is sitting less than 40 million kilometers from Earth at its closest, near enough that on a clear night you can see it without a telescope, the brightest thing in the western sky after sunset, beautiful and still and utterly hostile to every living thing that has ever existed. The precise path by which Venus arrived at its current condition is one of the genuinely open questions in planetary science. Some researchers argue that Venus may never have had an effective silicate weathering drawdown mechanism, perhaps because it lacks the abundant liquid surface water that the weathering reaction requires. Others argue for a scenario in which Venus once had something more like a functioning climate system, perhaps even oceans early in solar system history, and that the steady brightening of the young sun pushed it past a tipping point from which no feedback could recover it. The Magellan spacecraft, which mapped the surface of Venus with radar in the 1990s, found a world geologically young in a puzzling way, its craters distributed in a pattern that suggests the surface has been repaved within the last few 100 million years, not continuously and gradually, the way Earth's surface is constantly renewed, but perhaps all at once, or in great catastrophic pulses. This is the catastrophic resurfacing hypothesis, and it describes a planet that may not have steady volcanic outgassing balanced by steady weathering drawdown, but instead a planet that builds up heat and internal pressure over millions of years until the whole surface erupts in an enormous geological convulsion, releasing enormous quantities of gas, and then sits quiet again. Not a thermostat at all, a pressure cooker that vents periodically and catastrophically. Whether this is actually what Venus does is debated, but the idea is instructive because it shows that the range of behavior available to a planet without working plate tectonics is not just a single failure mode. It is a space of possibilities, and the two ends of that space look like the two worlds we can see from our own. One froze, one baked. Both did so because the recycling stopped working. Earth sits between them in the middle, and the reason it sits in the middle, the reason it has sat in the middle for 4 billion years, is the thermostat. The Walker-Hayes casting feedback, described in a paper published in 1981, is the single most important thing, keeping Earth in the habitable zone, more important in the long run even than our distance from the Sun, because that distance alone would not have been enough when the Sun was 30% dimmer. The weathering thermostat is why Earth did not freeze solid under the faint young Sun. It is the reason that when ice ages came and the planet cooled, they were ice ages and not extinction events for the whole biosphere. Carbon dioxide kept accumulating from volcanic outgassing even as the cold slowed weathering, until the warming tipped the balance and the ice retreated. The feedback worked. It always worked until we ask what happens in a world where one side of it is removed. Now remove that side and the planet tips toward the ice if it starts warm and weathering capable, toward the fire if the CO2 has nowhere to go and the surface grows too hot and dry for the reaction to run at all. Two different failure modes from the same missing mechanism. Two different worlds, one on each side of us in the night sky, each one a ghost of what Earth might have been, or might yet become, in the very longest reaches of time. Let us stay with the ice for a while longer, with the slow world cooling not from outside but from within its own chemistry, and let us think about what else changes when the plates stop moving and the mountains have nowhere new to come from.
Orogeny. It is one of geology's finer words. It means the birth of mountains, the process by which rock is lifted, buckled, folded, thrust upward against the pull of gravity by forces acting at the edges of colliding plates.
The Himalaya exist because the Indian subcontinent, riding its plate northward at a rate of a few centimeters a year, is still pressing into the southern edge of the Eurasian plate, has been pressing into it for roughly 50 million years, and has raised the Tibetan Plateau and the Great Range that forms its southern wall in the process. The Andes exist because the Nazca Plate is being subducted beneath the western edge of South America, and the compression and volcanic activity associated with that subduction have pushed the land upward in a nearly unbroken wall along the spine of a continent. The Alps, the Rockies, the Atlas, the great mountain ranges of the world, each one is a record of a collision, a subduction, a boundary event, a place where plates met, and the only direction for the rock to go was up. Stop the plates, close the file on collisions. The mountains that exist in this moment, the Himalaya at their current height, the Andes as they stand tonight, remain standing in the sense that nothing has struck them down, but something has struck them from above, from below, from the side, since the moment they first rose, and that something is erosion, and it does not have an off switch. Rain falls on rock. That is the beginning of erosion. The rain is slightly acidic because of the carbon dioxide dissolved in it, and that acid attacks the minerals in the rock, slowly weakening the crystal structure, slowly releasing fragments, gradually producing the stuff called soil when it mixes with organic material, and sand and gravel and silt when it washes away. Frost wedges into cracks and expands and splits the rock. Rivers carry sediment downhill, glaciers grind, wind abrades. The whole surface of any elevated landmass is under continuous patient attack from every direction, and the attack does not pause because the uplift has stopped. It simply continues, now unopposed. How fast does this happen? The denudation rates, the rates at which material is stripped from the surfaces of active mountain ranges, are measured in fractions of a millimeter per year, in slower ranges and several millimeters per year, in faster ones. These are not large numbers, they do not feel dramatic, but when you multiply even half a millimeter per year by 100 million years, you get 50 kilometers, and most mountain ranges are not 50 kilometers tall. The Himalaya at their tallest peak, Everest, reach about 8.8 kilometers. Erosion running unopposed at even modest rates would, over timescales of tens to hundreds of millions of years, work through that height entirely. The word for what remains is peneplain. It comes from the Latin for almost, and the plane that those words together describe is something geologists use to name the theoretical end state of a landscape that has been eroded long enough without being rebuilt, a surface worn down to near the level of the sea, low and rolling and without significant relief. The stumps of former mountain ranges visible only as slightly harder rock, standing a few meters above the surrounding flatness because they happen to be made of more resistant material. William Morris Davis, working in the late 19th and early 20th century, developed this idea of the cycle of erosion, a sequence that moved from the youthful landscape of sharp peaks and deep valleys through maturity and into the flat old age of the peneplain. Davis was working before plate tectonics was understood, and his model was refined considerably once we understood that landscapes are not simply aging in one direction, but are instead driven by the competition between tectonic uplift and erosional downcutting. Take away the uplift and the cycle runs to completion. The peneplain is not a metaphor, it is the destination of any landscape given enough time and no resupply. But there is a subtlety here that rewards some care, and that subtlety is isostasy. Mountains do not simply sit on the surface of the earth the way a pile of sand sits on a table, they float. The continental crust, which is less dense than the mantle beneath it, sits in gravitational equilibrium with the mantle, the way ice floats in water, with a large proportion of its bulk submerged as a root extending down into the mantle. A high mountain range has a deep crustal root, the way a tall iceberg has a deep underwater extension, and as erosion strips material from the top, the reduction in weight allows the whole mass to rise slightly, the way an iceberg rises in the water if you shave ice off its top. This process is isostatic rebound. It means that the lowering of a mountain range is not simply a one-to-one correspondence between how much rock is removed and how much height is lost. For every meter of material stripped from the surface, the range rebounds somewhat, rising back to partial compensation. The root is always trying to maintain equilibrium with the material above. This is why ancient mountain ranges like the Appalachians, which have not had major tectonic activity for hundreds of millions of years, still have modest topographic relief even after all that time, why they are not yet a peneplain, why they still have ridges and valleys and elevations measured in the hundreds to low thousands of meters rather than being truly flat. Isostatic rebound is not a rescue, it is a delay. The rebound rises in proportion to the weight removed, but the system as a whole is still losing material, still losing rock to the rivers and the sea, still working steadily toward the lower elevation. It extends the timeline. It is perhaps a mercy in the deep time sense, a slowing of the inevitable, a way in which the mountains of this still world persist rather than vanishing quickly. The Himalaya would not be gone in 1,000,000 years. They might be significantly reduced but still recognizable, still impressive by any human standard. But over tens of millions of years, over 100 million years, the rebound mechanism cannot overcome the arithmetic of erosion, because the rebound does not create new rock from nothing. It only redistributes what remains, and what remains is constantly leaving in every river, in every grain of sediment settling on the ocean floor, in every cubic meter of silt deposited in a delta. There is also the question of the ocean floor beneath these deltas. The sediment that erosion carries to the sea does not vanish. It settles on the ocean floor, building the thick deposits of the continental margins, the deep sea fans, the abyssal plains. In a world with working plate tectonics, this sediment has a fate. It gets carried on the ocean floor toward a subduction zone. It gets dragged down, it gets recycled into the mantle, and eventually returned in some form through volcanic activity. Without subduction, the sediment simply accumulates. The ocean floor gradually fills, in a geological sense, with the ground-down remains of continents that are no longer being rebuilt. The ocean basins themselves change character as the sea floor ages without renewal, growing colder and denser and subsiding slightly, altering the geometry of the ocean, the distribution of shallow and deep water, the patterns of circulation. What would the continental surface look like in this world after that long, slow work? Think about it carefully, and you begin to see something almost peaceful in its strangeness. The great mountain barriers that today divide climates and direct winds and separate the ecosystems on either side of them would be gone, replaced by low, rolling, deeply ancient rock. The kind of surface that today you find only in the geologically quiet hearts of continents, the cratons, those billion-year-old shields of worn basement rock that form the stable cores of the continents and that have sat quiet and undisturbed for so long that they are almost flat, almost peneplain already. The whole planet would, in this far future image, look something like a craton. Low relief. Ancient rock. Wide, shallow continental seas where the ocean had spread over the flattened land because without mountains rising to maintain continental freeboard, the ocean would encroach, and the distribution of land and sea would be something quite different from the world we know. Not a water world, not an ocean covering everything, but a world of very shallow, very extensive, very warm continental shelf seas, shallow enough to be well lit from above, warm enough perhaps to sustain certain kinds of marine life even as the land was becoming less hospitable. There is something almost meditative about this image if you hold it at the right distance, with the right timescale in mind. Not a world destroyed, a world worn smooth, a world that has exhaled its mountains and its relief into the ocean, slowly, across an unimaginable span of years, not with violence, but with the patient and continuous work of water and ice and gravity. The planet would still be turning, the ocean would still be moving, the sun would still be rising and setting, but the silhouette of the land against the horizon would be different in every way, lower and rounder and older looking, and the air above it would be thinner in the one gas that makes the plants grow. And the plants by then would be very much diminished or gone. That is the deep strangeness of the freeze path, the CO2 crash path. When you follow it to its conclusion, the world would not go cold, not at first, not in the dramatic, icy way. It would go quiet, it would go thin. The biological engine would lose fuel, not fire. And the flatness of the land and the thinness of the air would come together in a world that was geologically ancient and biologically simplified and very, very still. Framed in deep time, which is the only honest frame for this conversation, none of this happens in days. It does not happen in years or centuries or even the first million years after the imagined stillness descends. A million years after plate tectonics stopped, Earth would look almost exactly as it does tonight. The mountains would still be there, the volcanoes would be quieter, the arcs cooling, but the hot spots would still be erupting. The carbon dioxide would be fractionally lower, measurably lower if you had sensitive enough instruments, but not lower in any way a living thing would notice. The world would be almost exactly itself. The change is in the direction, the change is in the fact that the mechanism which would have corrected any drift, the feedback that would have pushed the atmosphere back toward a stable middle range, is now broken. The drift does not correct. It accumulates, and given enough time, enough patience, enough of the vast and unhurried arithmetic of geology, the drift becomes a destination. 2 planets in this same solar system already reached their destinations, and they are there tonight, visible in the same sky as the stars you might look up at before closing your eyes, burning their own quiet lessons into the dark. The mountain building has stopped. The carbon is leaving the sky. The land is rounding slowly toward the sea. And the world is still, in ways it has not been still since before the first fish crossed onto land, before the first fern unrolled in the light, before the Himalaya lifted, and before the Andes rose, and before any of the ranges that shape the wind and the rain and the path of every river had been raised from the quiet floor of whatever ocean came before them. This is the world not in ruins, this is the world in retirement, and retirement at the planetary scale is a very long and very gradual and in its way very beautiful thing, even if beauty is not the word you would naturally reach for when you understood what it meant for the chemistry of the air and the productivity of the soil and the fate of every species that depended on both. The thermostat runs, the carbon falls, the mountains wear down toward the sea, slowly, isostasy buying them time, but not saving them, the peneplain waiting at the bottom of millions of years of patient rain. And somewhere in this picture, there is still the question of the deep interior, the iron heart of the world, and whether the shield that deflects the solar wind is holding, whether the compass still points, whether the invisible cocoon that wraps this planet and turns the most energetic particles of the sun aside is still working. That is the next question, and it is the counterintuitive one, because the thing everyone worries about first, the magnetic field, the thing that in every disaster movie is always the first to go, is actually, in this scenario, the last to fail. And the reason why is sitting 5,000 kilometers below you, in the dark, in the liquid iron of the outer core, where a different kind of engine is running, powered not by the movement of plates at all, but by something far older and far more fundamental, the slow and inexorable freezing of the innermost heart of the world. Hold that thought. We are not finished with the surface yet. There are still the oceans to consider and the volcanoes that remain, and the strange and specific lesson of a volcano on another planet that grew to 22 kilometers tall for exactly the reason we have been circling all along. The seafloor, which you might picture as a stable, permanent thing, a fixed basin that holds the water the way a bathtub holds its bath, is actually one of the most transient surfaces on the planet. Not transient on any scale you would notice in a lifetime or even across the whole span of recorded human history, but transient in the deeper accounting of geological time, where the ocean floor turns over completely in roughly 100 to 200 million years, new crust constantly being born at the mid-ocean ridges and old crust constantly being consumed at the trenches. The Atlantic floor spreading apart at roughly the pace your fingernails grow. The Pacific floor sliding beneath the Asian and American margins with a slowness that makes glaciers seem impetuous. All of it moving, all of it cycling, all of it part of the same vast circulation that keeps the planet's surface young. And now the plates have stopped. The mid-ocean ridges, those long, sinuous mountain ranges on the ocean floor, the mid-Atlantic ridge running like a seam down the center of the Atlantic basin, the East Pacific rise stretching across the floor of the Pacific, a global system of underwater mountains roughly 60,000 kilometers long in total. All of them go quiet. Sea floor spreading requires the plates to be pulling apart, the mantle welling upward into the gap, cooling, solidifying, and joining the edge of the diverging plate as new ocean crust. It is a remarkably clean process when you understand it. Rock rises, melts, cools, moves outward, eventually descends. The ridge is where the birth happens, the trench is where the burial happens, and now neither is happening. What remains is the ocean floor as it was at the moment of the stoppage. And this floor is not uniform. Ocean crust has an age, and that age is recorded in everything from its temperature to its depth below the ocean's surface. Young ocean crust, freshly minted at the ridge, is hot and buoyant. It rides high, which is why the mid-ocean ridges are ridges, but they are high because the rock beneath them is warm. As the crust moves away from the ridge and ages, it cools, it contracts, it becomes denser, and it sinks deeper. Very old ocean crust in its last few tens of millions of years before subduction sits in the deepest trenches of the ocean. The depth of the seafloor, if you mapped it carefully, would tell you the age of the rock, a clock written in bathymetry. With spreading stopped, the floor continues to cool. The ridges, now silent, lose their source of warmth and gradually subside. The distinction between young ridge and old basin begins to blur as everything cools toward the same ambient temperature. The thermal structure of the ocean floor, which previously carried real information about the movement history of the plates, slowly anneals toward uniformity. And the sediments, which were always accumulating, the slow rain of dead plankton, of clay particles, of wind-blown dust settling through the water column, continue to fall. They have always been falling. They fall at rates of centimeters per 1,000 years in the deep ocean, barely perceptible, a geological snowfall. But with no subduction to drag them down into the mantle and no spreading to push them sideways, they simply pile up. Millennia by millennia, the ocean floor gets blanketed. The ridges, already subsiding, become buried. The distinction between ridge and abyssal plain softens, then eventually disappears, as sediment fills the topographic lows and drapes the former highs. The ocean basins are aging in a way they have never aged before, because previously their age was always bounded. Old crust was always being removed and replaced. Now there is a ceiling on what young ocean crust even means, and over time, that ceiling simply recedes into the past. And the ocean itself, above all this, changes in response to changes in the seafloor, in the mountains, in the chemistry of the water. The ocean's chemistry is not static. It is responsive, sensitive, in conversation with the rock it sits upon and the rivers that feed it and the atmosphere above, with the mountains wearing down and delivering their loads of sediment and dissolved minerals to the sea, and with no new seafloor spreading, delivering the particular chemistry of fresh basalt to the water, and with the carbonate chemistry of the ocean shifting as the atmospheric CO2 changes above it. The sea is a different ocean than the one you know, not overnight, not in any single human generation or 100 generations. But over the vast, patient unrolling of geological time, the sea becomes quieter, simpler, less rich and colder, or warmer, depending on which direction the thermostat has tipped. There is a stillness beginning to settle over the world, not silence in any literal sense. Wind still moves, rain still falls, rivers still run. But a particular kind of geological noise, the noise of a living, active, plate-moving world, is fading. The earthquakes are going quiet. This is something worth sitting with for a moment, because earthquakes feel like a permanent feature of existence. They have been shaking the ground for as long as there has been ground to shake. They are woven into human mythology, into the architectures of cities, into the engineering calculations of every bridge and building in seismically active regions. Japan builds for them. Chile plans around them. The west coast of North America lives with the constant low-level awareness of them. But the vast majority of Earth's seismic energy, the large earthquakes, the ones that reshape coastlines and trigger tsunamis, is concentrated at plate boundaries. The subduction zones, where one plate dives beneath another, produce the largest earthquakes ever recorded, including the 1960 Valdivia earthquake in Chile, the most powerful in the instrumental record. The transform faults, where plates slide past each other, produce the kind of fault system you find beneath San Francisco. The collision zones, where continents grind into each other, produce the long, slow, deep seismicity of a mountain range still being built. All of these are plate boundary phenomena, and with the boundaries frozen, they cease. What remains are the intraplate earthquakes, the quieter, less frequent tremors that occur not at the edges of plates but within them, where ancient fault lines still harbor residual stress, where isostatic adjustments continue as ice loads shift and erosional weight is removed, where the interior of the continent responds to changes in loading and temperature over time. These earthquakes are real. They happen today, far from any plate boundary, in the middle of continents, in regions people think of as seismically calm, but they are smaller and less frequent by several orders of magnitude than the boundary events. The world becomes, seismically speaking, a much calmer place, not a silent one, but one where the great geological drumbeats of the deep structure, the subduction zone megaquakes, the collision front tremors, the spreading ridge microseismicity all fade away, leaving only the occasional intraplate murmur of an old wound in the rock that hasn't quite healed. If you could feel the planet through the soles of your feet, the way some people claim to feel the deep hum of infrastructure or the far-off vibration of traffic, you would notice that something was different, that a layer of vibration you had never consciously registered was gone. The Earth, underfoot, would be stiller than it has ever been in 4 billion years of its history. And that stillness would not feel like peace, exactly. It would feel like the kind of quiet that follows a very large and very long conversation. The silence of something that has been speaking since before memory and has at last fallen still. The volcanoes are not all gone. This is important to understand, and it is one of the places where the story diverges from the simplest version people imagine. The simplest version goes, tectonics stops, and all the volcanoes stop with it. But that is not quite right, and the reason it is not quite right illuminates something fundamental about the different engines that drive volcanic activity on Earth. There are two broad categories of volcanism, and they have different power sources. The first is plate boundary volcanism. This is the kind that creates the volcanic island arcs, the Aleutian Arc stretching from Alaska across the northern Pacific toward Russia, a curved chain of volcanic islands that exists because the Pacific plate is sliding beneath the North American plate along that margin and driving magma upward. The Mariana Arc, further west in the Pacific, where the Pacific plate dives beneath the Mariana plate with such violence that the Mariana Trench, the deepest point in the ocean, has been carved into the sea floor. Japan sitting above subducting plates on multiple sides, one of the most volcanically active nations on Earth, for exactly this reason. The Andes along the western spine of South America, where the Nazca plate is subducting beneath South America and driving the volcanism that makes that mountain range not only tall but also thermally alive. The Lesser Antilles in the Caribbean, where the Atlantic plate is descending beneath the Caribbean plate and producing a string of volcanic islands that includes Martinique, where Mont Pelée killed a city in 1902, and Montserrat, where Soufrière Hills is still active today. All of these are driven by subduction. Subduction brings water down into the mantle along with the plate, water bound in hydrated minerals in the subducted rock. As the slab descends and heats up, that water is driven out of the minerals and rises into the mantle wedge above. Water lowers the melting point of rock, a fact that seems counterintuitive, that adding water to rock makes it melt more easily, but it is one of the foundational facts of petrology, the science of how rocks form. And so the water rising from the descending slab causes the mantle above it to melt, even though the temperature might not, on its own, be high enough to do so. That melt rises. It collects in magma chambers. It erupts. The arc volcano exists. With subduction stopped, no plate is descending, no water is being driven into the mantle, no melt is being generated by that mechanism. The arc volcanoes, deprived of their supply, go cold, not instantaneously. There may be residual magma in chambers that could fuel a few more eruptions over thousands or tens of thousands of years. The deep plumbing of a volcanic system has inertia, but the supply is cut. And over geological time, the same deep time we have been measuring everything else in, the arc volcanoes go extinct one by one as the last of their inherited magma cools and solidifies, and the conduits that once carried molten rock to the surface seal themselves shut. Japan becomes, over this vast span, a geologically quieter island chain. The Aleutians cool. The Andes, already struggling with the cessation of uplift, lose their thermal component as well. The volcanoes that still crown the high peaks go silent. The Cascades in the Pacific Northwest, driven by subduction of the Juan de Fuca plate beneath North America, go dark. The entire arc and trench system of the Pacific Rim, that ring of fire that encircles the Pacific Basin and has given the Earth so much of its most dramatic volcanism, falls silent as arc after arc loses its fuel supply and fades. This is a profound change in the character of the planet, but it is not the end of all volcanism. The second category is hotspot volcanism. driven not by plate boundaries but by mantle plumes, rising columns of hot rock that originate deep in the mantle, possibly at the boundary between the mantle and the outer core, and punch upward through the overlying rock regardless of what the plates above are doing. A mantle plume is, in a sense, indifferent to the plates. It rises because it is hot and buoyant. It reaches the base of the lithosphere, the rigid outer shell, and spreads laterally, melting the base of the rock above it and driving magma upward. The resulting surface expression is a hotspot, a place where volcanic activity occurs, not because of plate boundary processes, but because of this deep plume of rising heat. The canonical example, the one that almost everyone has encountered at some point, is Hawaii. The Hawaiian Islands are the surface expression of a hotspot, a mantle plume sitting beneath the Pacific plate. The plate is moving slowly northwestward, and as it moves, the hotspot burns through it, creating a new volcanic island, building it up from the ocean floor through eruption after eruption until it breaks the surface, and then, as the plate moves on and carries that island away from the hotspot, the eruptions cease on that island and begin on the next patch of ocean floor that has drifted over the source. The result is the Hawaii Emperor Seamount Chain, a long trail of volcanic islands and submerged seamounts stretching from the currently active Big Island of Hawaii northwestward across the Pacific, each older than the one to its southeast, a record of the plate's motion written in the ages of the volcanoes. The bend in the chain, where the Emperor Seamounts curve to a more northerly trend than the Hawaiian portion, marks a change in the direction of plate motion tens of millions of years ago, preserved in volcanic rock like a geological compass needle. This chain exists because the plate moves, the hotspot is fixed. The plate slides over it, and the volcanoes are strung out behind, like footprints in the ocean floor. Now stop the plate. The island chain stops growing. No new island forms to the southeast of the Big Island. The existing islands continue to be carried very slowly as erosion and isostatic subsidence gradually reduce them. But the volcanic activity concentrates entirely on the island directly above the hotspot, because there is nowhere else for it to go. The plume is still rising. The heat is still there. But the crust above it is not moving away to expose fresh seafloor. All that heat, all that magma, all that volcanic energy piles into one place. And over time, deep time again, millions of years, that one place becomes extraordinary. This is not a hypothetical. We have the example. It exists right now on the next planet, outward from us. On Mars, which has not had anything resembling Earth-style plate tectonics for at least the last several billion years, there is a volcanic province called the Tharsis Bulge, a broad, elevated region roughly the size of North America, and within it, the largest volcano in the solar system, Olympus Mons. It rises approximately 22 kilometers above the surrounding plains. To put that in terms your body can hold, Mount Everest rises about 8.5 kilometers above sea level. Olympus Mons is nearly 3 times that height, measured from its base on the Martian plains to its summit caldera. Its base is so wide that if you were standing on the plains at its edge, you would not be able to see the summit. The curvature of Mars itself would hide it below the horizon. It is not just the tallest volcano in the solar system, it is almost incomprehensibly large by any measure we apply to mountains. And the reason it is that large is precisely the reason we have been circling all along. The Martian crust did not move. On Earth, the Hawaiian hotspot builds a volcano, then the plate moves on and the volcano is carried away from the heat source and goes extinct, and a new one starts. The energy is distributed. The chain is the signature of distribution of a moving plate spreading the volcanic work across thousands of kilometers of ocean floor. The tallest individual Hawaiian volcano, Mauna Kea, measured from its base on the ocean floor, is actually comparable to or even exceeds Everest in total height. But Mauna Kea is not 22 kilometers tall, measured from its surroundings, because it sits on ocean crust that is itself subsided, and because the chain effect means the hotspot's energy was shared with all the other islands before it and will be shared with islands after it. On Mars, there was no sharing. The plume rose, the crust sat still above it. Eruption after eruption, over hundreds of millions of years, piled onto the same location. The caldera at the summit of Olympus Mons is actually a nested set of calderas, the record of multiple collapses following major eruptions, the geological diary of a volcano that has been returning to the same spot again and again for an almost incomprehensible span of time. The Tharsis bulge itself is the product of so much volcanic rock piled onto the Martian surface in one region that it actually warped the planet's rotational axis. The sheer mass of the volcanic province, accumulated over billions of years of stagnant lid volcanism, was heavy enough to shift Mars's orientation in space, a volcano so big it tilted a planet. This is what a stationary lid does to volcanic topography. Instead of a chain, it makes a colossus. Iceland is another hotspot, one that happens to sit on a mid-ocean ridge, a combination that makes it unusually active and the only place in the world where a mid-ocean ridge system breaks the ocean surface as dry land. With plate tectonics active, Iceland is being pulled apart slowly as the mid-Atlantic ridge spreads, even as the hotspot beneath it adds extra volcanic material. If the plate stopped and Iceland's ridge component went quiet, only the hotspot component would persist. Iceland would no longer be splitting, it would be piling up. The volcanic output would concentrate rather than being distributed along the ridge. Yellowstone, in the interior of North America, sits above what is interpreted as a mantle plume or hotspot system beneath the North American plate. It is not an arc volcano driven by subduction. The Snake River Plain, stretching across southern Idaho to the northwest of Yellowstone, is the trail the hotspot has burned through the North American plate as the plate moved over it. The same logic as Hawaii, the same chain of footprint signature. If the plate stopped, Yellowstone would stop migrating and would simply accumulate volcanic activity in one place indefinitely. So the world without plate tectonics is not a world without volcanoes. It is a world with a different kind of volcano, no arcs, no subduction-driven chains, no ring of fire, but the plumes persist because the plumes are powered by the interior heat of the planet, and the interior heat of the planet is not directly dependent on whether the plates are moving. Where there are mantle plumes, there will still be eruptions, quieter in some ways, without the water-driven explosive character of subduction zone volcanoes, but persistent. And because the crust above them is no longer moving, the volcanic energy accumulates in one place, building upward and outward, constructing the kind of enormous, gently sloped shield volcanoes that Olympus Mons represents, rather than the steep, explosive stratovolcanoes of an island arc. The planet's volcanic face changes. It doesn't go dark, it consolidates. This change has consequences that run deeper than topography. The arc volcanoes were important contributors to the carbon cycle we spent so much time tracing earlier in this account. They were part of the outgassing system that returned CO2 to the atmosphere after subduction had carried it down. Hotspot volcanoes also degage carbon, but the character and rate of that outgassing is different, and the total quantity is uncertain. The plumes tap different parts of the mantle that may carry a different chemical signature than the subducted carbonate-laden material that arc volcanoes were processing. The resupply of CO2 to the atmosphere from plume volcanism is not negligible, but it is not the same pipeline as the subduction arc system. And so the carbonate-silicate cycle's resupply arm, already compromised by the death of the arcs, is running on reduced capacity from the plumes alone. The thermostat still has one arm reaching for CO2, but the other arm is now trying to push back with less force than before. Whatever plume volcanism contributes is less than the full arc plus ridge plus diffuse system that operated when the plates were moving. The drawdown continues to outpace the resupply, and the slow lean toward the freeze continues. And then there is the matter of what continental weathering is delivering to the ocean, and what that delivery does to life in the sea. This is a thread that connects the flattening continents to the chemistry of the ocean in a way that is easy to miss if you are thinking about geology in purely physical terms. Mountains as rock, erosion as the removal of rock, without holding in mind that the rock is chemistry and the chemistry is biology. Phosphorus is one of the essential nutrients for life. Not glamorous, not the element that gets named in headlines, but foundational. Phosphorus is required for adenosine triphosphate, ATP, the molecule that carries energy within every living cell, in every organism on Earth without exception. It is required for DNA and RNA, the molecules that carry and transcribe the genetic information that makes life continuous. Without phosphorus, cellular life as we know it cannot function. And the ocean's supply of phosphorus comes, overwhelmingly, from the weathering of continental rock. Rivers carry it, sediment delivers it. The mountains, being eroded, are releasing it into the hydrological system and from there into the sea. In a world with active plate tectonics and active mountain building, continental weathering is vigorous. Fresh rock is constantly being uplifted by orogenic processes, the collision of India into Eurasia building the Himalaya, new rock being brought up to the surface, exposed to rain and rivers, chemically attacked and dissolved and carried to the sea. The supply of weathering products, including phosphorus, is sustained by the constant renewal of the mountains. When the plates stop and no new mountain building occurs, the weathering continues. Rain still falls, rivers still run, but it is drawing on a finite and diminishing reserve. The mountains are being consumed without being restocked. The peneplain is the end point, a low, nearly flat surface where the rock being weathered is old, chemically depleted, the most soluble minerals long since removed, leaving behind the most resistant residues. The flux of nutrients from the continents to the ocean, the rate at which phosphorus and other essential elements are being delivered by rivers to the sea, declines over geological time as the mountains shrink and the fresh rock faces that provided the richest source of weathering products are slowly buried or rounded away. The ocean receives less. The phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web that collectively produce a substantial fraction of the oxygen in Earth's atmosphere, that are the first link in the chain that feeds everything from krill to whales. The phytoplankton depend on that nutrient supply. They pull nitrogen and phosphorus and iron and silica from the water. When the supply diminishes, their populations diminish. The productivity of the ocean falls, and everything built on top of that productivity, the zooplankton that graze on it, the fish that eat the zooplankton, the marine ecosystems that have been running on the ocean's photosynthetic foundation for hundreds of millions of years, all of it responds to that reduction at the base. The connection between a mountain being worn down in what used to be Central Asia and the abundance of life in the middle of the Pacific Ocean is not obvious when you are standing on either one. But the river carries the message, the ocean receives it, the plankton read it, the web of life transcribes it upward all the way to the surface, where the chain ends in everything that breathes and eats and dies. A world with smaller, older, less weathered continents is a world with a less productive ocean. Not immediately, not next year, or next century, or even next millennium. But in the accounting of geological time, which is the only accounting that matters in this thought experiment, the nutrient flux from land to sea is a slowly closing tap. The ocean quiets, the productivity dims, the food web thins. And this is happening at the same time as the atmospheric CO2 is falling, at the same time as the plants on land are feeling the drawdown tightening around them. The crisis is not arriving from one direction. It is arriving from every direction at once, slowly, over timescales that no individual organism would register. A planetary scale convergence of a dozen different feedbacks, all pointing toward the same general reduction in the conditions that make the world as alive as it is. The mountains erode, the ocean quiets, the arcs go cold, the plumes persist, concentrated, building their enormous shields in places where the crust has stilled above them. The great earthquakes have ceased, the ridges have subsided beneath their blanket of sediment. The world is geologically calmer than it has been since before the first plate boundary formed billions of years ago, and that calm is not comfort. It is the calm of a system losing its circulation, a body losing its metabolic rate, a planet in the long process of finding a new and simpler equilibrium. Somewhere in all of this, in the carbon falling, in the mountains lowering, in the ocean quieting, in the volcanism changing character, there is still the question of the deep interior. The question that we parked earlier, deliberately, because it deserved its own space and its own careful attention. The magnetic field. Everyone who encounters this thought experiment worries about the magnetic field first. It is the visceral fear. The invisible shield goes down, the solar wind floods in, the atmosphere is stripped, the surface radiation becomes lethal, and the story ends with something that looks uncomfortably like what happened on Mars. This is the fear that the disaster movies have fed, and it is not entirely wrong. The end state, if you trace it far enough, does look something like that. But the sequence is wrong, the timing is wrong, and the mechanism, when you understand it, is one of the most counterintuitive and in some ways most beautiful facts about how the deep interior of this planet actually works. Because the magnetic field, in the scenario we are considering, does not die when the plates stop. It does not even start failing immediately. And the reason for this becomes clear when you understand where the field actually comes from and what is actually powering it. The geodynamo, the engine that generates Earth's magnetic field, lives in the outer core, not the crust, not the mantle, not anywhere near the plates. The outer core is a shell of liquid iron and nickel sitting roughly between about 2,900 kilometers and 5,100 kilometers below the surface. A liquid metal ocean, moving, convecting, circulating in patterns that are organized by Earth's rotation through the Coriolis force, the same force that organizes hurricanes and ocean gyres at the surface, but acting here on liquid iron at temperatures and pressures that no surface analogy can quite capture. This convecting liquid metal generates electrical currents. The electrical currents generate magnetic fields. The magnetic fields, in turn, influence the convection of the metal in a complex feedback. The geodynamo is a self-sustaining system, a system that, once running, tends to keep itself running, amplifying and organizing its own field through the interaction of flow and magnetism in the liquid iron. The simulations that Glatzmeyer and Roberts ran in 1995, one of the first full three-dimensional computational models of the geodynamo, captured this self-sustaining character, showed how the field could maintain itself, could reverse periodically as the flow patterns in the outer core shifted, could produce the complex dipole-dominated but imperfect structure that the real field exhibits. None of this involves the plates. The plates are at the surface. The outer core is 5,000 kilometers down, beneath the entire thickness of the mantle, separated from the surface by a column of silicate rock that is itself nearly 3,000 kilometers deep. The plates and the outer core are as remote from each other as they could be while still being inside the same planet. Whatever is happening to the lithosphere, whether the plates are moving, whether they have stopped, whether the surface is being reshaped by erosion and the loss of mountain ranges, none of it directly affects the liquid iron of the outer core on any time scale that matters for the immediate life of the dynamo. The dynamo is powered by two things. The first is thermal convection. The outer core is hotter than the mantle above it, and heat flows outward, driving convection in the liquid iron the same way that heat drives convection in a pot of water on a stove. Hot material rises, cool material sinks. Circulation is established and maintained by the temperature gradient. The second, and arguably the more important on longer timescales, is compositional convection. The inner core, the solid iron ball at the center of the Earth, roughly the size of the Moon, is slowly growing. It has been growing for billions of years as the planet gradually cools, and iron at the very center crystallizes out of the liquid. As iron freezes onto the inner core's surface, the light elements that were dissolved in the liquid iron, oxygen, sulfur, silicon, are expelled back into the outer core. These lighter elements are buoyant, they rise, and as they rise, they drive vigorous convection in the outer core, convection that is particularly effective at sustaining the geodynamo. This is compositional convection, and it is going on right now continuously as the inner core grows by a fraction of a millimeter every year. A glacially slow expansion that nonetheless, over billions of years, has produced an inner core of considerable size and has been powering the geodynamo's compositional engine throughout. This engine is not connected to the plates, it is connected to the temperature of the core and the slow crystallization of iron at the center of the world. Stop the plates and the compositional engine keeps running. The inner core keeps growing. The light elements keep rising, the outer core keeps convecting, the dynamo keeps generating the field. The magnetic cocoon around the planet survives the stopping of the plates, at least in the immediate sense, at least on the timescale of millions of years. This is the counterintuitive reprieve. The compass still points, the solar wind is still deflected, the Van Allen belts still exist, those radiation-trapping shells in the magnetosphere that protect the surface from the most energetic particles the sun throws out. Life, insofar as it can still sustain itself on a world with falling CO2 and quieting ocean productivity and eroding mountains, does not face the additional catastrophe of losing its magnetic shield in the same geological instant that everything else begins to fail. But there is a deferred link, and it is subtle, and it matters on the very long time scales that the rest of this account has been operating in. And that link runs through the mantle. The mantle is the intermediary between the surface and the core. It is the enormous shell of silicate rock, roughly 2,900 kilometers thick, that separates the outer core from the crust above. The mantle is solid on the timescale of seismic waves. Shear waves pass through it, proving it is not liquid, but it is not solid on the timescale of geology. On timescales of millions of years, the mantle flows. It convects slowly, carrying heat upward from the core mantle boundary to the base of the lithosphere above. This mantle convection is, in a deep sense, the engine of plate tectonics itself. The plates are, partly, the surface expression of this mantle circulation, dragged and pushed by the convecting rock below. And the mantle is the pathway through which the core loses its heat. The core is hot, the mantle is cooler. Heat flows from core to mantle across the core mantle boundary, down the temperature gradient, and it is this heat loss from the core, this flow of heat upward through the mantle and eventually to the surface, that maintains the temperature gradient in the outer core that drives the thermal component of the geodynamo's convection. Here is where the plate tectonics connection re-enters subtly. Cold oceanic slabs descending through subduction zones carry cold material deep into the mantle. They are, effectively, cold injections into the mantle from above, refrigeration. They cool the mantle. A cooler mantle is more efficient at drawing heat out of the core at the core mantle boundary. A more efficient heat extraction from the core keeps the temperature gradient in the outer core steep, which drives vigorous thermal convection in the outer core, which helps sustain the dynamo. When the plates stop and subduction ceases, those cold slab injections stop. The mantle, no longer being refreshed from above with cold material, warms up slowly. It acts more like a lid, insulating the interior rather than actively drawing heat out of it. This is the stagnant lid effect. The lid traps heat. The mantle temperature beneath the lid is higher than it would be in an actively recycling system, and a warmer mantle is less efficient at drawing heat out of the core. The heat flow across the core mantle boundary decreases. The temperature gradient in the outer core that drives thermal convection becomes shallower. The thermal component of the geodynamo weakens. This does not happen on geological timescales of millions of years. It happens on timescales of billions of years. The compositional convection powered by the inner core's slow freezing continues regardless, but over very long times, as the mantle warms under its stagnant lid and the core mantle heat flow diminishes, the dynamo's overall energy budget tightens. The field may weaken. Its geometry may become less stable, more prone to the kind of excursions and reversals that already punctuate the geomagnetic record. Eventually, in a future so remote it makes even the geological timescales we have been discussing seem brief, the dynamo could be undermined by this thermal strangulation from above. It is not the first thing to fail, but it is not immune. And we have the example. We have the example because the experiment has already been run, not in a laboratory, not in a computer simulation alone, but on a world you can see from your backyard on any clear night. Two worlds, in fact, one to the left of us and one to the right, in the rough geography of the inner solar system, and they bracket the two ends of what we have been describing across this long, slow journey through deep time. They are not hypothetical. They are there, hanging in the dark, and what happened to them is written in their surfaces and their skies with the same patient permanence that limestone writes the history of ancient seas. Begin with the one that froze. Mars is a small world, about half the diameter of Earth, and it sits farther from the Sun, and those two facts, its size and its distance, are part of the story. But they are not the whole story. Mars is a stagnant lid planet. Its surface is one continuous rigid shell, a single lithospheric plate covering the whole globe, with no subduction zones driving slabs into the interior, no sea floor spreading drawing new material up from below, no convergent margins crumpling into mountain chains. The lithosphere just sits there, thick and unmoving, the way a frozen pond sits in winter, sealed from below. And the consequences of that arrangement are visible from orbit. They are visible from the surface. They have been read over decades by orbiters and landers, and the patient work of planetary scientists piecing together what a world looks like when it runs this particular experiment to its conclusion. Start with the volcanoes, because the volcanoes make the stagnant lid principle almost physically tangible. The Hawaiian Islands are a chain, a long archipelagic necklace strung across the Pacific, with the oldest, most eroded islands to the northwest and the newest, still erupting island to the southeast. They exist in a line because the Pacific plate is moving over a fixed mantle plume, a hotspot rooted deep in the mantle that punches up through the lithosphere and melts its way to the surface. The plate carries each volcano away from the hotspot like a slow conveyor belt. The island builds, erupts for a time, then gets carried off as the next island begins forming behind it. The chain is a record of motion. Each island is a timestamp. The geometry of the chain is the geometry of the plate's movement written in basalt and coral and deep submarine slopes. Now stop the plate. If the Pacific plate simply ceased to move, the hotspot would not turn off. The mantle plume would still be there, still delivering heat, still melting its way upward. But Instead of the melt reaching a new location every million years or so, it would reach the same location over and over. The same spot on the crust would receive eruption after eruption, pulse after pulse of magma, building not a chain of modest islands, but a single growing mountain. The volcanic edifice would accumulate. It would build up and outward and upward, decade after geological decade, spreading its flanks across the ocean floor and piling its summit higher and higher into the sky, limited only by the structural strength of its own base and the rate at which erosion could compete with construction. And that is, in precise and literal terms, what happened on Mars. The Tharsis Bulge is a volcanic plateau on Mars roughly the size of North America. It is a raised region of the crust, thousands of kilometers across, that appears to have formed over an immense span of time as repeated eruptions piled material in the same location, because the crust never moved over the underlying heat source, because there was no plate to carry the eruptions away from the hot spot. The magma came up and came up and came up again, and the crust rose and thickened and spread under the weight of it. And sitting on top of the Tharsis Bulge, there is Olympus Mons. Olympus Mons is approximately 22 kilometers tall, measured from its base. That is nearly 3 times the height of Everest above sea level. It is the tallest volcano in the solar system. It is wider than France, its base spreading roughly 600 kilometers across, with a caldera at the summit large enough to contain the city of London many times over. It is not a sharp peak, it is more like an enormous, gently sloping shield, a rounded dome rising so gradually from the surrounding plains that if you stood at its base you might not immediately perceive the mountain at all. The curvature of Mars would hide its upper slopes over the horizon. You would only feel the ground rising, slowly, imperceptibly, as you walked, and the air, already thin, would thin further with each kilometer gained. Olympus Mons exists only because the ground beneath it never moved. That is the direct consequence of the stagnant lid. That single fact, that the crust sat still while the mantle plume continued to deliver, built the solar system's tallest mountain. It is counterintuitive in the way of very elegant things. The absence of motion produced the most extreme topography. The plate that never moved piled up the mountain that no moving plate could ever build. On Earth, movement distributes the eruptions. On Mars, stillness concentrated them. So the stagnant lid is not simply a quieter version of plate tectonics. It produces different landscapes, different accumulations, different extremes. But Olympus Mons is not the end of the Mars story, and the volcanoes are not the most consequential thing that the stagnant lid took from that world. The magnetic field is. Roughly 4 billion years ago, Mars had a global magnetic field. The evidence for this is still visible today, encoded in the ancient southern highlands of Mars, in a form that the Mars Global Surveyor spacecraft first detected in the late 1990s. When the spacecraft's magnetometer swept across the southern highlands, with the oldest, most heavily cratered terrain on Mars, it detected bands of alternating magnetic polarity in the crust. Stripes of rock magnetized in one direction, then the next direction, then back again, repeating in a pattern that is eerily familiar to anyone who knows what seafloor spreading looks like on Earth. On Earth, as new oceanic crust forms at mid-ocean ridges, it is magnetized in whatever direction the geomagnetic field happens to be pointing at that moment. When the field reverses, as it does periodically on timescales of hundreds of thousands to millions of years, the new crust forms with the opposite polarity. So the seafloor preserves a record of every reversal, a kind of magnetic barcode spreading symmetrically away from the ridge axis. When oceanographers first detected these magnetic stripes in the mid-20th century, it was one of the most powerful pieces of evidence for seafloor spreading, and by extension, for plate tectonics itself. The stripes in Mars's southern highlands look, to some researchers, like something analogous like the fossil of a process that once moved crust around, that once spread new material from some ancient spreading center, that once recorded the reversals of an ancient Martian dynamo in the rock as it formed. The interpretation is not universally agreed upon. Planetary science rarely produces certainty on questions this old and this difficult. But the possibility is seriously considered that Mars, very early in its history, may have had something resembling early plate tectonics, or at least an active crustal recycling process before it froze into its stagnant lid configuration. If so, then Mars did not begin as a stagnant lid world, it became one. And when it became one, the dynamo eventually failed. The details of exactly why and exactly when involve the same logic we traced at the end of the previous movement: a stagnant lid insulating the interior, mantle heat no longer escaping efficiently, the core mantle heat flow diminishing, the thermal engine of the geodynamo weakening. The timing on Mars appears to be around 4 billion years ago, in the deep Noachian era, when the planet was still geologically young. The fields switched off, or drained away slowly. The exact history is difficult to recover from the rock record, and Mars was left without its magnetic shield. The consequences were not immediate. They unfolded over hundreds of millions of years. But they were total. Without a magnetic field, there is nothing to stand between the planet's atmosphere and the solar wind. The solar wind is a continuous stream of charged particles, protons and electrons, flowing outward from the Sun at several hundred kilometers per second. On Earth, those particles are deflected by the magnetosphere, the invisible force field generated by the geodynamo, which funnels them toward the poles and keeps them from interacting directly with the bulk of the upper atmosphere. We see the traces of this deflection in the auroras, the shimmering curtains of light at high latitudes where the particles do penetrate, but the deflection keeps the main body of the atmosphere intact. On Mars, once the shield failed, the solar wind began picking up atmospheric particles directly, ion by ion, molecule by molecule. The process is called atmospheric sputtering and ion escape, and it is exactly what it sounds like. The solar wind, interacting with the unshielded upper atmosphere, gradually strips particles away and flings them into space. It is not a dramatic process. It does not happen all at once. It is slow, patient, relentless, geological in its patience, and over hundreds of millions of years it removes the equivalent of most of a planet's atmosphere. We know this is happening on Mars today. The MAVEN spacecraft in the Mars atmosphere and volatile evolution mission reached Mars in 2014 and has been measuring atmospheric escape rates ever since. It can detect the ions leaving the Martian atmosphere, can track the rate at which the solar wind is stripping the air, and can model how those rates have varied over time as the Sun was younger and more active. The numbers it has returned confirm what the thin air of Mars already suggested. Mars lost its thick, early atmosphere to the solar wind after its magnetic field failed, and it is still losing atmosphere today, just very slowly, because most of what could be lost has already been lost. The Martian atmosphere today is about 1% of Earth's atmospheric pressure at the surface. It is mostly carbon dioxide, which is itself a clue, a remnant of what was once a much thicker envelope of gas, but so thin that liquid water cannot persist on the surface under current conditions. The pressure is too low, water would immediately evaporate or freeze. The surface temperature averages around -60 degrees Celsius. It is a cold, dry, thin-aired world, and it arrived at that state in part because it lost its magnetic shield, and it lost its magnetic shield because its dynamo died, and its dynamo died because its interior cooled under a stagnant lid and could no longer drive the convection in the outer core that generates a geomagnetic field. This is the chain. It is not a short chain. Each link takes hundreds of millions or billions of years to propagate, but it is a chain, and Mars walked it to the end. And Mars also ran a version of the carbon thermostat failure that we described earlier. Without active plate tectonics and subduction, the deep carbon cycle slowed dramatically. Volcanic outgassing declined as the interior cooled, and the crust thickened, and the mantle plumes delivered less and less material to the surface. The weathering continued. Wind and frost and the occasional liquid water during warmer periods early in Mars's history continued to interact with silicate rock. But the resupply of carbon dioxide through volcanism could not keep pace with the loss through atmospheric escape and slow weathering. The thermostat, already weakened by the stagnant lid, was then fully overwhelmed by the stripping of the atmosphere itself. Mars could not maintain its early warmth. It transitioned from a world that may once have had liquid water on its surface, rivers, and perhaps lakes and seas in the Noachian period, into the frozen, desiccated place it is today. Mars is the freeze end of the spectrum. It is what you get when the thermostat fails slowly, when the atmosphere is lost patiently, when the interior cools and the lid thickens and the dynamo fades and the carbon cycle winds down to a whisper and then to nothing over billions of years. It is not a catastrophe in the thriller sense. It is a quiet ending, spread across timescales so long they become almost meditative to contemplate. Mars did not die in a day or a year or 1,000 years. It exhaled its warmth across geological eons, and what remained when that exhalation was complete was the cold, still, reddish desert we see today, as beautiful in its way as it is inhospitable. And then there is Venus. Venus sits on the other side of us from Mars, closer to the Sun, and it is almost exactly Earth's size. Its diameter is about 95% of Earth's. Its mass is about 82%. In the early history of the solar system, Venus and Earth probably formed from similar material under similar conditions, and for a time they may have been more similar than they are now. Some models suggest Venus may once have had liquid water on its surface. Some models suggest it may once have had a magnetic field. The deep past of Venus is hard to read because the surface is geologically young, relatively speaking, and the planet's thick, hot, acidic atmosphere makes surface observation difficult. What we know about Venus comes largely from the Magellan spacecraft, which reached Venus in 1990 and spent 4 years mapping the surface with radar, bouncing radio waves through the opaque clouds, and constructing a detailed topographic and geological map of the entire planet. What Magellan revealed was a world of extraordinary volcanic character. Vast lava plains covering most of the surface, towering shield volcanoes, strange features called coronae and tesserae that have no direct parallel on Earth, and very few impact craters. The absence of many craters suggests the surface is geologically young, reshaped relatively recently. Estimates based on crater counts suggest a mean surface age of perhaps a few 100 million years, though the uncertainty in such estimates is large. But what is striking is that the young surface does not appear to be the result of steady, continuous plate tectonic recycling in the way Earth's surface is renewed. Venus does not appear to have the linear chains of mid-ocean ridges, the consistent patterns of seafloor spreading, the orderly subduction zones that characterize Earth's tectonic system. It looks instead like a stagnant lid world, with a thick, unmoving lithosphere covering a hot interior, that may periodically undergo something more dramatic than steady-state recycling. The hypothesis proposed by researchers studying the Magellan data is called catastrophic resurfacing. The idea is that Venus's lithosphere, unable to subduct because it is too thick and too buoyant under the high surface temperatures, and lacking the organized tectonic system that Earth has, may instead build up internal heat over hundreds of millions of years, heat generated by radiogenic decay and mantle convection below the lid, until the lid itself becomes gravitationally unstable, founders, and is replaced by a global outpouring of volcanic material in a geologically brief but intense episode. An overturning. A global resurfacing event that buries the old surface under kilometers of fresh lava and resets the crater clock. And then the lid reforms and the heat builds up again, and eventually the next overturning comes. If this is correct, Venus's geological history is not a steady rhythm like Earth's, but a punctuated one. Long, quiet periods under a stagnant lid, interrupted by brief, catastrophic episodes of global volcanic activity. It is a different mode of the stagnant lid regime, and it may explain the young surface age without requiring plate tectonics. Whether or not the catastrophic resurfacing hypothesis is precisely correct, and it is still debated, with the full picture not yet settled, the overall condition of Venus's surface is not in question. Venus is a stagnant lid world in its current state, and the consequences for its atmosphere and climate are written in the numbers. The surface temperature of Venus is approximately 465 degrees Celsius. That is hot enough to melt lead, hot enough to soften zinc, hot enough that any organic chemistry of the kind that underpins life as we understand it would be destroyed in moments. The atmospheric pressure at the surface is about 92 times Earth's. 92 atmospheres, so dense that the air itself behaves almost like a fluid. The atmosphere is composed almost entirely of carbon dioxide with clouds of sulfuric acid at high altitude that reflect most sunlight back into space, keeping the surface from absorbing much solar energy directly. And yet the surface is far hotter than simple solar heating can explain. The heat is retained by the greenhouse effect of all that carbon dioxide. A runaway greenhouse in which the CO2 traps heat so effectively that the surface temperature soars far above what the planet's distance from the Sun alone would produce. Venus is a world where the carbon thermostat has no working drawdown arm. On Earth, remember, the thermostat operates because silicate weathering draws CO2 out of the atmosphere and locks it into carbonates, which are then subducted into the mantle and returned as volcanic outgassing. Both arms of the feedback are active. On Venus, in the current configuration, there is no effective subduction to complete the cycle, and the extreme surface conditions, the crushing pressure, the searing heat, create an environment where the silicate weathering reactions that work on Earth may not proceed in the same way. Carbon dioxide accumulates in the atmosphere. It cannot be removed at the rate it would need to be removed to prevent the greenhouse from running away. And so it accumulates further, and the temperature rises, and the temperature rise makes the environment even more hostile to the chemistry that might otherwise draw the CO2 back down. Venus is the bake end of the spectrum. It is what you get when the carbon thermostat fails in the other direction, when CO2 accumulates rather than draining away, when the atmosphere thickens rather than thinning, when the greenhouse strengthens rather than weakening. Mars froze, Venus burned. Two planets, one on each side of us in the solar system, Earth's nearest neighbors in space, and they represent the two failure modes of the planetary thermostat we have been tracing through this long, slow exploration. Earth sits between them, and Earth sits between them precisely because its thermostat has both arms working. Plate tectonics draws carbon down through subduction, and plate tectonics releases carbon back through arc volcanism and metamorphic outgassing. The balance between those two processes has never been perfect, and the Earth's climate history shows the evidence of its imperfections, ice ages and greenhouse periods, and mass extinctions driven in part by perturbations to the carbon cycle. But the feedback has remained intact. When CO2 rose, weathering accelerated. When CO2 fell, weathering slowed. The negative feedback held. For 4 billion years, through the brightening of the sun and the drifting of the continents and the evolution and extinction of entire biospheres, the thermostat held the planet within a range where liquid water was possible, where chemistry could unfold. where something as improbable as a thinking animal could eventually appear and look up at the sky and wonder about it. That is the gift of plate tectonics, not the earthquakes. Those are the cost. Not the volcanoes. Those are the side effects. The gift is the thermostat. The gift is the recycling. The gift is the feedback loop that has quietly, invisibly, patiently kept the planet from sliding off into the cold that took Mars or the heat that took Venus, and it will not last forever. This is where we arrive at the deepest layer of the meditation, not the thought experiment of a sudden stop which has been the vehicle for this entire journey, but the slow, real, geological truth about Earth's future. The thought experiment of stopping the plates overnight was a way of making visible what those plates actually do by imagining their absence. But the real version of this scenario does not require imagining. It is coming. It is written into the physics of how planets age. The engine of plate tectonics on Earth is heat. The heat in Earth's interior comes from two sources: the residual heat of the planet's formation, left over from the violent accretion and differentiation of the early Earth 4.5 billion years ago, and the ongoing decay of radioactive isotopes, uranium, thorium, and potassium-40, scattered through the mantle and crust, releasing heat as they decay. These radiogenic heat sources are the long-burning fuel rods of the planet's interior, and they are not inexhaustible. Uranium-238 has a half-life of about 4.5 billion years. Thorium-232 has a half-life of about 14 billion years. Potassium-40 has a half-life of about 1.25 billion years. These are long time scales, longer than the current age of the Earth, but they are finite time scales. The fuel decays, the heat output falls. Over billions of years, Earth's interior will cool. The mantle will become stiffer and more viscous as it cools, because the viscosity of mantle rock is strongly temperature-dependent. Cooler rock resists flow more, the way cold honey is thicker and slower than warm honey. A cooler, stiffer mantle is harder to drive into convection. Harder to drive into convection means less vigorous plate tectonics. Less vigorous plate tectonics means slower subduction, slower spreading, slower recycling of the carbon cycle, less arc volcanism to return CO2 to the atmosphere. And at some point, models suggest this is perhaps a billion or a few billion years in Earth's future, though the exact timing depends on assumptions that are genuinely uncertain. Plate tectonics may slow to a near halt, or transition into a regime that looks more like what we see on Venus or Mars today. The thermostat will begin to fail, not overnight, not in a decade or a century, but over hundreds of millions of years. The feedback loop will weaken as the volcanism that forms one of its two arms declines. The CO2 that weathering keeps drawing out of the atmosphere will find no volcanic pathway back in, and Earth will begin its slow slide toward whichever end of the spectrum its particular circumstances favor. Some models suggest the CO2 level in Earth's atmosphere will drop below the threshold where C3 plants can photosynthesize, around 150 parts per million, within perhaps 500 million to a billion years, even accounting for the natural tectonic processes still operating. The slowdown of volcanism as Earth cools would accelerate this drawdown, starving the atmosphere of the CO2 that plants require. The base of the food web would erode. The biosphere would contract, simplify, retreat, possibly toward a world dominated only by the most metabolically flexible microorganisms, the kinds of creatures that were running the planet before complex multicellular life appeared. And through all of this, the magnetic field would be weakening for the reasons we traced: the mantle lid retaining heat, the core mantle heat flow declining, the thermal convection in the outer core gradually losing energy, the dynamo slowly losing its ability to sustain the organized currents that generate the field. The inner core would still be freezing, still releasing the compositional buoyancy that drives the other component of the geodynamo, and so the field would not go silently or instantly. But eventually, on timescales of billions of years, the combined cooling of the interior and the eventual exhaustion of the compositional driving force would let the field fade. And without the field, Earth's atmosphere would be exposed to the same patient stripping by the solar wind that took Mars's air. Whether Earth ends cold like Mars or hot like Venus, or something in between, depends on factors that are genuinely not fully resolved in current planetary science. The Sun is itself changing, brightening by roughly 1% every 100 million years as it burns through its hydrogen fuel, and the brightening Sun adds heat to the system in ways that complicate the CO2 drawdown picture. A warmer Sun might push the balance toward a Venus-like outcome, more evaporation, more water vapor in the atmosphere, a strengthening greenhouse, even as declining volcanism pushes toward a CO2 crash. The two forces might cancel for a time. They might not. The precise shape of Earth's geological ending is not known. What is known is that the ending exists, that the planet is not eternal in its current configuration, that the thermostat, which has run for 4 billion years, is running on a finite supply of the fuel that keeps it going, and that the fuel is decaying slowly but irreversibly, and that the planet is cooling slowly but irreversibly, and that the plates will eventually slow and then stop. Not because of any sudden catastrophe, but because the furnace inside will one day no longer be hot enough to drive them. Earth is, in this sense, on a very long arc toward the condition of Mars or Venus. It is not close to that arc's end. The time scales involved are comparable to the current age of the universe, but it is on the arc. The thought experiment we have been running throughout this night is not a fiction. It is a description of where the planet is going, slowed to the point of imperceptibility, stretched across billions of years, unfolding so gradually that no living thing could ever perceive it. And this is why the thought experiment is worth sitting with. Not because the plates are going to stop tomorrow, or in any human future, or in any timescale a civilization can plan against, but because understanding what plates do, and what the absence of plates has meant for Mars and Venus, and what the slow fading of plates will mean for Earth, is a way of understanding what kind of thing a habitable planet is. The writers Peter Ward and Joe Brownlee, in their work on the conditions required for complex life, gave this question the name of the rare Earth hypothesis. The idea is that the particular combination of factors that makes Earth suitable for complex life, its location in the solar system, its large moon, its active geology, its functioning carbon thermostat, its long-lived magnetic field, its liquid water oceans, the interplay among all of these may be unusual enough in the galaxy that planets like Earth are genuinely uncommon. The stagnant lid worlds and a Mars-like and Venus-like world may be far more typical. The question of how common plate tectonics is on other planets is one the field of planetary science is still working to answer, because we do not yet have the observational tools to detect plate tectonics on worlds beyond our solar system. But within our own solar system, Earth appears to be the only planet with active Earth-style plate tectonics right now. Mars is stagnant, Venus is stagnant or episodically overturning. The Moon has no active geology to speak of. Mercury's interior is partially molten but geologically quiet. The outer planets and their moons have their own forms of geological activity, driven by tidal heating in some cases, Io's sulfur volcanoes, Europa's possible subsurface ocean, but nothing that looks like the organized, continuous, subduction-driven plate recycling that Earth sustains. The thermostat that has kept Earth habitable for 4 billion years may be genuinely unusual, and it is still running. Right now, as you breathe slowly in the dark, and the thoughts drift and the edges of sleep begin to blur the outlines of things, the planet beneath you is in motion. Somewhere under the Pacific, a slab of oceanic crust is sliding down a subduction trench, carrying its cargo of limestone and carbonate sediment toward the heat of the mantle beginning the long journey that will end, eventually, in a burst of volcanic breath from an arc somewhere. From the Aleutians, from Japan, from the Andes, from the countless smaller cones and fissures along the world's volcanic arcs, carbon released and returned to the sky. Somewhere under the Atlantic and the Pacific and the Indian Ocean, new crust is forming at the mid-ocean ridges, welling up from below, spreading outward, building the seafloor that will one day carry its own limestone cargo into the next subduction zone. The mountains of the Himalaya, still rising fractionally each year as India presses north into Eurasia, are being carved by rain and river and ice even as they rise, sending their dissolved minerals into the ocean, feeding the weathering feedback that draws CO2 down, maintaining one arm of the thermostat that keeps the planet's temperature within the narrow range where liquid water pools and living things can persist. The system is old. It is 4 billion years old, at least in its broad outlines, and it has survived ice ages and asteroid impacts and the brightening of the sun and the drifting of the continents into every configuration a geologist has been able to reconstruct. It has survived because the feedback is self-correcting, because when it tips toward cold, it warms itself, and when it tips toward warm, it cools itself, and because the two arms have remained intact. Remove one arm and that self-correction becomes impossible. The planet loses its ability to steer. It drifts slowly toward whichever end of the spectrum the physics of its particular moment favors. Mars drifted to one end, Venus drifted to the other. Earth is still in the middle, still being held there by the slow, patient, invisible machinery of its moving plates, its subduction zones, its arc volcanoes, its weathering rivers, its carbonate seafloors riding down into the dark and returning as breath. This is what the plates are. Not just the engine of earthquakes and mountain ranges and volcanic islands, though they are all those things. They are the mechanism by which the planet regulates itself. They are the difference between a living world and a dead one, or at least the difference between a world that has held the conditions for complex life steady across geological time and a world that lost those conditions early and never recovered them. They are the infrastructure of habitability, running so quietly and so slowly beneath everything that the creatures living on the surface, the animals and the trees and the microbes, and the eventual thinking animals who began to wonder about these things, mostly do not perceive them at all. You do not feel the plates moving. You do not feel the carbon returning through volcanic breath, or the limestone sinking into the mantle, or the mountain range being carved by tomorrow's river, while today's collision still pushes it upward. These are processes too slow for a human nervous system to register, and too vast for a human mind to hold fully, and they run at depths and on timescales that belong to a different kind of time altogether. Deep time, geological time, the slow time of a planet aging through billions of years. But they are there. They are happening, they will keep happening for 1 billion years, or perhaps a few billion, and then they will slow and the carbon cycle will weaken, and the thermostat will lose its ability to compensate, and the planet will begin its long, unhurried slide toward the stagnant condition that Mars and Venus have already reached. The interior will cool, the mantle will stiffen, the dynamo will dim, the atmosphere, unshielded, will thin, and whatever was living on Earth's surface at that unimaginably distant moment, if anything still is, will face a world that is slowly becoming less hospitable, the habitability draining away the way warmth drains from a stone left in the dark after a long day in the sun. It is not a catastrophe, it is not a horror, it is the nature of rocky planets to form, to heat, to sustain geological activity while their interiors are warm enough, and to cool slowly over billions of years into quietness. It is the natural arc of things. Mars reached the end of that arc early, partly because it is small and lost its interior heat more quickly, Venus may be somewhere in a middle stage, its episodic resurfacing a sign of an interior still active but arranged differently, not quite able to sustain the organized steady-state recycling that Earth manages. Earth is further along than Mars was at the same age, its interior still vigorous enough to drive the plates, but not forever. There is something restful in this perspective, not comforting in the sense of being free from melancholy. There is melancholy in the deep time scales, in the thought of a planet exhaling its last warmth across millions of silent years, in the fate of a biosphere slowly starved of CO2 and magnetic shelter. But restful in the way that very large things can be restful when you contemplate them honestly. The universe is old, the planet is old. The processes that sustain life here are ancient and enormous, and they have been quietly running long before anything capable of appreciating them existed to do so. And they will run for a long time yet, longer than any timescale a human civilization can meaningfully relate to before they slow. Tonight, right now, in this moment, the system is intact. The plates are moving. The volcanoes are breathing. The rivers are dissolving silicate rock and carrying carbonate to the sea. The magnetic field is turning, generated by iron convecting in the liquid outer core 5,000 kilometers beneath the ground, organized by the Coriolis force of a spinning world, holding back the solar wind. The mountains are being built and worn simultaneously in the slow dance of uplift and erosion that has been going on since the first continental crust appeared and the first rain fell. All of it running, all of it quietly, invisibly holding the planet in the place where life can exist. That is the story of what the plates do and what would happen if they stopped, and what the worlds next door tell us about the two ends of the spectrum and what the planet's far future holds. It is a story told in deep time, in carbon and silicate and iron and heat, in the language of a planet conducting its own existence across billions of years. It is not a story with a tidy ending. The real story never is. But it has a shape, and the shape is one of a planet balancing between extremes, held in place by the machinery of its own moving surface, for as long as the heat in its interior can sustain that machinery, and that is, by any measure of time that matters to the creatures now living on it, a very long time indeed. The stone beneath you is still warm. Tie off here at the wisdom docks. The tide will wait till morning.